Good morning students. Today we'll discuss about Hall effect. We'll see what is Hall effect. So when a current carrying conductor is placed in magnetic field, means if I take a conductor, I'll consider a conductor which is applied with electric field. This we call it as current carrying conductor. So the conductor which is applied with electric field is placed in magnetic field. So how this electric field and magnetic field is applied? They are applied perpendicular to each other. Then a voltage is developed. A voltage is developed in a direction perpendicular to both electric field and magnetic field. So electric field applied on x-axis. Magnetic field is applied on y-axis. Then voltage is produced in a direction perpendicular to electric field and magnetic field. This phenomenon is called as Hall effect, and voltage developed is called as Hall voltage, which is represented by VH. So see here, when a current carrying conductor is placed in magnetic field, a voltage is developed across the conductor perpendicular to both current and magnetic field. This phenomenon is called as Hall effect, and voltage developed is called as Hall voltage. Now we can see Hall effect for P-type and N-type semiconductors. Hall effect for P-type and N-type semiconductors. So see here, for P-type semiconductor, if we see here, I have applied electric field on x-axis and magnetic field on y-axis. Then Hall voltage should be developed in a direction perpendicular to both electric field and magnetic field. So what happens? What are the majority charge carriers in P-type semiconductors? Holes are the majority charge carriers. Holes carry which charge? Positive charge. So here, as the hole voltage is developed in a direction perpendicular to both electric field and magnetic field, here the holes are moving from phase 2 to phase 1. The voltage developed is measured with the help of voltmeter. With the help of probes we have connected to this slab voltmeter. Okay. Now the holes are moving from right to left. Means Hall voltage is developed in a direction along z-axis. If Hall voltage is positive, then it is called as P-type semiconductor. Similarly in N-type semiconductor, what are the majority charge carriers? Here majority charge carriers are electrons. So these majority charge carriers will be moving because Hall voltage is developed along z-axis. So they will be moving from phase 2 to phase 1. That is from right to left. Here the voltmeter shows the negative deflection. If Hall voltage is negative, it is of N-type semiconductor. If Hall voltage is positive, it is of P-type semiconductor. Okay. So in P-type semiconductor, when electric field and magnetic field are applied at right angles to each other, the holes experience a force from right to left, that is mutually perpendicular to both electric field and magnetic field. They are moving from right to left. Okay. So their holes are accumulated on phase 1. The probes connected from phase 1 to phase 2 measures the Hall voltage. Okay. If voltmeter indicates positive deflection, then it is of P-type semiconductor. Similarly for N-type semiconductors also. Okay. So Hall voltage, this Hall voltage will be positive. It will be positive for P-type semiconductor, and for N-type semiconductor Hall voltage will be negative. Okay. Now see here, determination of Hall coefficient. Hall coefficient is represented by RH. Now how to determine the expression for Hall coefficient? Okay. Now if I consider N-type material, what are the majority charge carriers in N-type material? In N-type material, majority charge carriers are electrons. So for this N-type material, I am applying with magnetic field and I am applying with electric field. So we are applying both electric field and magnetic field. So what happens? These electrons experiences force due to magnetic field and electric field. Now here V be the velocity of electrons. Now this electron is experiencing force due to magnetic field. So force due to magnetic field is given as minus BeV. E means charge of electron. Charge of electron is negative. That's why minus. Next, the force experienced by electron due to electric field is minus EH. E is charge of electron. B is magnetic field and EH is electric field. So at equilibrium, when the system is at equilibrium, the two forces will be equal. So minus BeV is equal to minus EH. So I can write it as EE get cancelled. EE get cancelled. I can write it as EH is equal to BV. Minus minus also get cancelled. Now we know this is equation number 3. We know current density J is equal to minus NeV. Current density J is equal to minus NeV. Here N represent concentration of electrons. N represents concentration of electrons. E represents charge of electrons. Okay. Now V is equal to minus J by Ne. I can write it as minus J by Ne. This is equation number 4. Okay. Now, so I got velocity V is equal to minus J by Ne. If I substitute here, so I'll substitute fourth equation in third equation. We'll get it as EH is equal to minus B J by Ne. So here Hall effect is described by Hall coefficient. Here 1 by Ne represents Hall coefficient. So RH is equal to 1 by Ne. This is equation number 6. So if I substitute this sixth equation in fifth equation, I'll get it as EH is equal to minus Bj. Instead of 1 by Ne, I can write RH. So RH is equal to minus EH by Bj, which is equal to minus Ne. So Hall coefficient will be negative. Hall coefficient will be negative for N-type semiconductors. Hall coefficient will be negative for N-type semiconductors. Now, if it is for P-type semiconductors, Hall coefficient will be positive and it will be represented as RH is equal to EH by Bj, which is equal to 1 by Pe. P means concentration of holes. P means concentration of holes. Okay. So if they ask in the examination to write about P-type semiconductors, here I have determined Hall coefficient for N-type. If they ask for P-type, so simply what you need to do, instead of electrons, you need to use the term holes and no need to write here negatives. All will be positive only. So instead of this small n, here n represent concentration of electrons. You can write in place of n, you can write P. So you will get the expression RH is equal to 1 by P. So this is about determination of Hall coefficient. Now we will go for applications of Hall effect or importance of Hall effect. Now what are the applications of Hall effect? First application is determination of type of semiconductor. By knowing Hall coefficient, we can find whether it is N-type semiconductor or P-type semiconductor, because for N-type semiconductor Hall coefficient is negative. For P-type semiconductor Hall coefficient is positive. So by knowing Hall coefficient, we can find whether it is P-type semiconductor or N-type semiconductor. Next, we can calculate concentration of electrons or holes, means calculation of carrier concentration. We know Hall coefficient RH is equal to 1 by Ne. So what is N? Concentration of electrons. So N is equal to, I can write it as 1 by ERH, means if I know Hall coefficient, I know the charge of electrons 1.602 into 10 power minus 19 coulombs. So if I know Hall coefficient, I can calculate concentration. Okay. So if Hall coefficient is known, what I can calculate? I can calculate concentration. First, I calculated, I have determined which type of semiconductor. Next, third one is determination of mobility of charge carriers. So we know formula for conductivity is Ne mu. Mu means mobility. Mu represents mobility. From this we can write mobility mu is equal to sigma by Ne, which is equal to sigma into what is 1 by Ne? What is 1 by Ne? RH, Hall coefficient, 1 by Ne. So if conductivity and Hall coefficient, if I know conductivity and Hall coefficient, I can find mobility. Okay. Next application is determination of magnetic flux density. So from the experiment, we know Hall coefficient RH is equal to VHT by IB. VH means Hall voltage. VH represents Hall voltage. T represents thickness of the slab. I represents current. B represents magnetic flux density. So from this, if I can write magnetic flux density as B is equal to, see here, from this expression I can write B is equal to, if I take this term this side and this term this side, we can write it as VHT by IRH. VHT by IRH means, see here, if I know here, if I know Hall voltage, thickness of the sample, current and Hall coefficient, I can find magnetic flux density. Okay. So if I know all these quantities, I can find magnetic flux density. So these are the applications of Hall effect. Thank you.